So today, definitely ask questions. Okay, so actually, let me start. So again, we're gonna look at complex decisions, as in decisions as the focus of our prediction model. So really, recent prediction models are not just stopping at a batch data, observational data given to you, and you want to just maximize prediction accuracy. So last class we looked at A/B testing and multi-arm bandits, contextual bandits. So these are all versions of the problem where they are not satisfied with just accuracy, prediction accuracy. In fact, making any prediction or estimating something about the environment is a secondary goal. The goal is to take decisions based on whatever you are estimating. So if you remember last time, if let's say you had bandit problem, where each arm had a mean reward, let's say in the stochastic setting, 3 mean reward values. We are not so much interested in estimating these reward values itself. So we don't care. We are let's say there was estimate mu hat, mu2 hat, and mu3 hat. Let's say we only cared about estimation. Maybe one strategy is pull the first arm or take the first decision 10 times, get some mean reward, maybe click through rate or something like that. Take the second second decision, maybe a different website, redesign, show it to 10 people, get a mean reward, and so on, right? So then you would get estimates of this, but that was not the goal. The goal was not just estimation. The goal was really tied to what decisions are you taking, or is the best decision you could have taken in hindsight. So that was the notion of reward, that was the notion of reward, cumulative reward, or the notion of regret. That in hindsight, if I knew that, let's say mu3 is the best guy, which was, let's say, mu star, then this is what I should have tried. This is what I should have shown to the users, or gotten interacted. This is the decision I should have taken in every round, basically. But I don't know that, and so I'll try different things. But I try different things not to focus on estimating, right? Not just focus on estimating these 3 numbers, because I'll run out of time. So there's some urgency in you trying to make decisions, because you're being evaluated at every time step, how off you are from what you could have done the best. Right? So maybe in first round you took the first decision, subscript 1, but you're supposed to take the third decision, right, in expectation. So you're off by mu3 minus mu1 or mu star minus mu1. You're off by that amount. So there's some urgency aspect. Otherwise, you would just keep, you just learn, which is basically try the first one few times, second one few times, third one few times, and get an estimate, right? That's not what we're doing here. So that's a slight change in objectives. We are focused on decisions. That our decisions should, we want to narrow down. We want to. The focus is on decisions and the objective as well. Objective is now regret, not estimating these quantities well. Okay, that's the big change we saw last time. But I think towards the end of last time I was telling you that bandits are nice, A/B testing and contextual bandits are nice, but your decision to show or take an action has no influence on what happens next. Okay, and today's theme is going to be your decisions at any given round or time is going to influence what happens next. Okay, so that's going to be the running theme throughout the lecture. Okay, and people and you do some sort of learning. Even previous set of techniques, we call them learning problems, but really we were not focused on learning the mean rewards, for example. We were not really focused on learning the mean rewards. We were focused on taking the right sequence of decisions to minimize regret. So here also there's going to be reinforcement learning, but the learning aspect is really, we're not so much focused on, when you say learning, it's kind of, it's loosely used to say we are searching for what is the best decisions to take. Okay, what are the best decisions to take? It's like loosely interpreted as searching as well here. And we're going to look at this variation, which is going to be more realistic than the ones, or takes into account that actions have future influences into account. And within that, we'll actually revisit an object which you guys might have seen 3 lectures ago, which is about Gibbs sampling. Okay, Gibbs sampling is based on this idea of having a Markov chain whose stationary distribution is the distribution from which you want to get a sample from. Okay, so here there's the word Markov there, so there's going to be a Markov chain as a base object, over which there will be some decisions as well, added on. So it's a slightly different object, but you'll revisit Markov chain. So maybe if you didn't understand Markov chain last time, try to kind of focus on that section, that part when I discuss about Markov chains, so you understand what it is. Okay, and then ultimately we'll look at one really old algorithm. I don't know how old it is, maybe 30-40 years old, which is an algorithm to learn what is the best decisions to take in each situation. Okay. So in each round you're faced with a situation. Remember the contextual binary setting. In each round, a situation, a context comes, and you need to take a decision. That's the interpretation of this in this modeling framework. Okay. So this is very quick overview of what we're going to do today, so that you are grounded on what different parts. We'll get into details pretty soon. Just to 2-minute motivation. I don't want to spend too much time on this because I think more than slides, there are some videos that I want to recap from the first lecture. So decision making is everywhere. If you just forget about prediction modeling, which is kind of the focus of this course, you just think of decision making. Decision making is no more, is not simple these days. Like if you're a business, for example, you really want to retain customers, you want to minimize customer churn. So there are different problems, and some of you doing capstone are also looking at certain types of problems, right? So ultimately, it's not whether you increase the prediction from 90-95%. It's about what is the impact on the business. Like operational decisions like inventory management, how much to stock for the future demand. If you're a retailer, things of that nature, and even more engineering style objectives like flying drones, autonomous vehicles, constructing autonomous vehicles, and so on. And a big part of that, building such complex, building such agents or software, basically, which can help you manage inventory, which can help you prevent customer churn by getting to those customers before they churn out. Or schedule transportation, resource allocate. So the softwares, they cannot be hand-tuned. They cannot be like, if this happens to this, if this happens to that. They cannot be written in a very programmatic way. So they have to do some sort of learning, and so that's where they are data-driven. And here are just some pictures of few more, I guess, decision problems. And you'll see that today's paradigm lets you have this data-driven rules or data-driven decisions that in this context do this, in this context do that. Okay, so that there's taking those decisions kind of helps you like minimize regret or maximize total reward collected or some such notion. Okay.
What is the complex decision
How many maybe it's expensive to run the trial. So actually medical trials is an example of the previous Band-Aid setting. So you don't want to waste time, placebo versus your drug. You don't want to waste time on placebo if the participant is expensive to come, or if it's a really rare disease, so you really have limited population. So you want to balance how much. Not how much to invest, but it's this addition of how many. What happened? Automatically changed. Okay. No, it's about how to. So you may have a finite population, a finite number of patients. So you wanna figure out from as few interactions with the patients as how to figure out the efficacy of the drug. Yeah, medical trials decisions are about which ones to go for trial 2, which ones to go for trial 3. Which drugs to develop. So there is a sequence of decisions that you take, and each one is an investment problem, essentially how much to invest. So you may even have a small portfolio problem with just within the pharma company. They may be trying out 10 different drug lines. Some may be promising, some may not be promising, and there's a lot of budget involved. Maybe not. There's some budget at the initial stage, and when the trial stage, there's a lot more money involved. So there's a lot of planning decisions to be made. Okay, and this one I just showed last time, that reinforcement learning, the paradigm that we're going to look at, is kind of important these days. A lot of research is happening, but but it may not be. So it's important in the sense of, okay, maybe it's used in games, okay, but that's just a curiosity. I mean, training agents to play games, or training agents to play, more complicated games. But it may also be an important component in engineering applications for sure, like autonomous driving. But it can also inform you of how to take complex decisions in other settings, like settings that I talked about, like operations and so on, where you may not do anything on pencil and paper, or not bring your domain knowledge to decide what decisions to take in which context. You can actually make an algorithm learn or figure out what decisions to take in different contexts. But of course, it's not free. You need to have some setup to kind of get to those decisions, get to those right decisions. So I'll discuss what all ingredients can make that happen. Okay. I think we saw some of these. So what's the most promising? Maybe this one. So this is a demo 2 years ago, last year, 2017. Maybe there's other demos. So this is a car without drivers, right? I mean, it has several components which are controlling its decisions. Its decisions just are steering and acceleration and so on. And there's a bunch of measurements. This is a completely engineering a physical system. But going from measurements all the way to decisions is not a prediction problem, right? You're not just saying, given the measurements so far, take a left or take a right or accelerate by X units. It's not a simple neural network going all the way from sensing to decisions. So the decision is actually going to be an outcome of a planning process. And planning typically means something like a Markov decision process that we will see today, or there are many other ways to do it. But there's actually a lot going on in terms of decision making than to just make a prediction. You've seen this, right? This was just a game. Somebody kind of made an RL agent or a reinforcement learning agent to play this game. And same thing with this, right? So the ingredient that I was saying, which is missing, which will make a software system come up with really good decisions of which decision to make in different contexts. That ingredient, the missing ingredient, or the key ingredient, will be a simulator. You need access to a simulator of the world. So you don't want to go to the world and say, I'm going to take inventory decisions like this, and that's going to affect my bottom line. That will be disastrous to your business. So you want to have a simulator of how the world behaves, and maybe take inventory actions and figure out how the world will change in the future, and take different inventory actions and so on. And based on that, you kind of search what is the best decisions taken in different contexts in the inventory management problem. So you need a simulator of the world, essentially, ideally. Okay. I mean, of course, if you don't have a simulator, you can try it in real world, but you should have a lot of money, a lot of budget to do that. Okay. And this was not needed. I think this is breakout. I think I've shown breakout before. So breakout is this Atari game, just to kind of ground that there's a game, and this is an agent which learned how to play the breakout game. It just has to break the bricks and gets a score at the top, sees the score and does this. So there's a CNN involved here. We'll get to the CNN stuff next lecture. Okay. So that will tie both decision making and the first part of the course, deep learning. But for today, we'll just focus on the decision making. Okay. It's good. So it's coming back here. And so before, again, this is the last slide before we jump into the details. So in terms of context, so what did we do last time? We looked at multi-on bandit, where you took an action and you got a reward. It could be stochastic. It could be non-stochastic. So if it's stochastic, the example that I drew before, like mu1, mu2, mu3, but you are not being evaluated in terms of estimating mu1, mu2, mu3, the mean rewards. You are being evaluated in terms of how well did you do in T rounds compared to just trying out the decision corresponding to mu star. Okay? That's the goal. Okay? So that was bandits. And then we said, okay, this seems quite limited. Let's say there's going to be a state or a context. Given the context, now tell me what action you're going to take. Given a certain type of, maybe your actions are recommending insurance policies, and then based on whether it's a student, a medical professional, or maybe maybe somebody in a risky profession, you're gonna take different actions, right? So the context determines actions here, but the context and the action both determine what reward you're going to get. Maybe the action that you took is incompatible with the person. Like maybe you show very high priced car to a student, then they will not click it. Maybe. So both the context and the action influence what reward you're going to get. What I think that this is a slide that I ended with last time is that this still is missing a piece, which is that the actions that you take has no influence on who comes next. Okay, maybe it's a sequence of customers that you come to your store and you serve them well, or you don't serve them well, has no influence on who's going to come next. But you can see that you can think about a different setting where maybe you serve a customer badly, they leave a rating on some review system, and then nobody else comes to your store anymore. Okay, so that would be a situation where your actions influence future states or future demand, for example. If you think of an inventory setting, and at the same time, both actions and the state influence what reward you get. It's the same setting, but with actions influencing future situations. Okay. I think for most of the lecture, I will use a setting which is more close to robotics, though. So we'll see how it goes, just to ground your mental picture. Okay. So let's start with reinforcement learning. So we have the same set of ingredients as before. So there is so in terms of naming, there is an environment, which just means that there is a user out there who's going to give me a reward, essentially. So there's a user out there, and we are the agent, and we take actions, right? And the key feature being that our actions may influence the future state that we have find ourselves in. Maybe lower demand, maybe higher demand. Okay. And agent gets a feedback signal. Maybe this feedback signal is not informative. That means that nothing happened. You served the customer, nothing happened, but 5 days later, the same customer did not come or something. Maybe they canceled the subscription 5 days later, something like that. So there will be a feedback signal. Maybe it's informative or non-informative, and maybe it's delayed. You may not get it in the same. So you serve a customer today, you may not get a reward. You may not get a reward signal or how good your service was immediately. Okay. So that's also a distinguishing feature compared to previous last lecture, because last lecture you took an action, you immediately got some number. Okay. So environment is what. So you interact with the environment and you change the state of the environment based on your actions. Okay. So that's the simple way to put it. So the environment could be demand distribution, and you change prices and you have different demands showing up. Okay, different, maybe lesser demand if you increase the prices, right? So that would be environment. And our goal is to select actions to maximize total reward. Okay, remember last time it was also total reward. It was a cumulative reward. It's the same thing. Okay, and because this aspect, this actions influence future. It's not clear what is the best way to approach this question, which is to maximize total reward. And reinforcement learning is a framework to kind of think of this problem from one point of view in a principled way. Okay. So let's see. So let me specify what the environment is. So I'm going to use AT to represent the actions of the agent. So AT just means in the teeth round. Teeth round could be the teeth day, teeth hour, or something like that. So AT is the action that I take. When I say I, is the agent takes and generates an observation ST plus 1. So because I took an action, something changes. Okay, so that is gonna be ST plus 1, and I get a reward RT plus 1. Okay, so why T plus 1 and why not T is just a convention. T index is time. Let's say it need not be time, but let's say it's time, and the current observation. So you make this decision based on the current observation, or current context, or the current state. Okay, so ST is actually just a state, context, or situation that you're in. You take an action AT, you get a new situation ST plus 1, and you also get a reward RT plus 1. So that's the 4 symbols: AT, ST, ST plus 1, and RT plus 1. Okay. And throughout this lecture, we'll just assume that some probabilistic relation holds, which is that we are in a stochastic setting. So states, so things, the reason why I wrote everything in capital letters is these are random variables. Okay, these 4 things are random variables, and we're gonna assume that this state sequence or the context sequence has a Markov property. Okay, by Markov property, all I'm saying, which is a way of saying that the conditional probability of a random variable and given another random variable has nothing to do with many other random variables. In this case, because these are sequence, like a time index sequence, all I'm saying is, given the current situation, my next situation has nothing to do with previous situations. So given the current situation, how I go to the next situation has nothing to do with what happened in the past. Okay, that's what it means to be Markov. We've seen this somewhere, I think in Gibbs sampling, right? We said given the observation, I can fill the next observation, but given the observation, previous observations don't matter in my sampling step. Okay. So that's the environment. What does the agent do? I mean, it's just a different point of view. Agent observes a sequence of these guys. I mean, agent observes ST, takes an action AT, right? Agent observes these guys, and agent's objective is to maximize rewards. Okay. Let's say I'm already at time t, then I just have to kind of maximize the rewards that I get from this point onwards, right? So this point I take action AT, I get a reward RT plus 1. I land somewhere, okay? In the sense of I see a different situation the next round, I take some other action and I get a different reward RT plus 2. Okay, so at this point I took an action AT, at this point I took an action AT plus 1, and so on. So my agent is just has to take actions, nothing else. That's the only thing I can control, right? But I need to take actions such that I kind of have this goal in mind, so that I can, in expectation, I collect as high reward as possible. Okay. So why expectation? Because some of these are random variables. Maybe the reward is I take an action and maybe they click or don't click, or demand comes or not doesn't come, things like that, right? And so these states you can think of as like a time series. Remember there was this Markov model, so this hidden Markov model, right? Something like that. So it's like a time series type of situation. So things are not IID. Okay. And one of the key features is going to be maybe because there is a long-term consequence of your action. Okay. Maybe there's a long-term consequence of your action. You may be willing to you're willing to trade off the current reward that you can potentially get, like immediately, like in this round, versus the gains that you could get later on. Okay. So this is a temporal trade-off that you can make. So, for example, it's a question of, let's say you have a dollar in your hand. You can spend it. You can invest it on some equipment improvement. Let's say you're running a business. You have $1 million in hand. You can improve equipment. That's your immediate action, and that may have an improvement in the production, right? Some improvement in production. Or you can set the $1 million for some other thing, maybe employee training or something else, and then have a long-term consequence of that, which is that because employees were retrained really well, even if the equipment is not a little bit 10% worse in terms of defects, employees are so good that you have ramped up production, something like that. I'm just saying that there is a consequence of things beyond your current decision that you take, and so you may have to trade off things. Okay. The trade-off need not be just at the same time, like should I buy A versus buy B, or should I take a decision A versus decision B, but this trade-off across time, that should I take action A and get a ton of reward right now, or should I take action B, get less reward, but hopefully in the future I'll get tons of more reward. Okay.
But wouldn't that be a risk? How do we know that the future reward is going to be better than the future?
So we are maximizing, so we have a precise objective, which is expectation. In expectation we need to collect these rewards. So there's this small number, gamma, think of it as some discounting, like I don't value future reward as much as the value current reward. But if this is the objective, there could be situations where you can see that the sum of all these guys may be higher than this. So maybe for action 1, this number is high, all these numbers are 0. And for action 2, this number is low, but all these numbers are high enough such that the summation is greater than the original.
So means the rewards would increase with time.
They may increase or decrease. So
So in case it decreases, then the trade-off will not work.
no, even if these numbers, let's say this is 1, let's say this is 10, and there are 10, so I put dot 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 here. So let's say it's a summation of 100 terms. Each one is 1 unit. Yeah, reward is decreased, but on summation it's higher. So okay, let's come back to this point to see if such a trade-off happens in some other example. Okay. So this is called being this is just being called myopic versus not myopic. Myopic means just you're immediately seeking reward or whatever, and you're being not myopic because you taking a different decision now has influence in getting more rewards later on. So just a quick point about reward. Reward is just a scalar number, indicates how well the agent is doing at a step t, right? And the agent's job is to maximize accumulated reward, just like in bandit setting. Okay. And
That expectation depends upon state also. Because how do you depend upon the state? Whether decision you make at a
yes, so we're gonna reveal what this expectation means at this point. Yeah, this captures all the randomness. So these are random variables, but for example, this random variable depends on where you land next. What is st plus 1? That's random, right? And your reward may depend on current state in action. So that then maybe this reward is fine. It's stochastic, but this reward depends on which next state you fell into, which is random, and then the reward itself may be random. So yeah, there's a lot of stochasticity. All that is compressed in this E. We'll see. We'll kind of try to unravel it a little bit. Okay. So for now, just think of E as capturing all the randomness. That's what to kill randomness, you take expectations or functions of your functions like that, right? So okay. So the goal sequence of actions to maximize total future reward. Actions are just decisions. That's why it's, same name. And the key point again, second time I'm repeating this, is actions may have long-term consequences. Okay. So is the components clear? There's an agent. There's an environment. Agents can only take actions, and our objective is to take actions to maximize total reward. That's it. So how many of you have done dynamic programming before? Just one? 3. Yeah, I mean this is related to dynamic programming in the sense it's the same. I mean, so in computer science there's a different focus, but dynamic programming is a different name for the same thing. But if in computer science the focus is on some smaller problems having the same structure as the bigger problems, and so you can solve the problem efficiently. So the focus is on use dynamic programming to compute things quickly. Here it's the same thing underlying, issue is the same. Here the focus is that actions have long-term consequences, so don't be myopic. So that's what dynamic programming also is. Okay. But those who do not have dynamic programming, this is related to dynamic programming. Definitely, you can just see Wikipedia afterwards. Okay, so let me just pictorially draw how the interaction is going to be. There's going to be an agent, tries an action 80. So sorry, the agent initially gets, at time t, he has seen the context, what situation is in, st. Maybe he has received a reward from the previous situation, maybe it's 0, doesn't matter. He receives something, which is st, responds with 80, okay, to the environment. As a consequence of that, he sees a new measurement. How is the environment now? Maybe the demand has decreased. Maybe I'm in a new location now, or things like that. Maybe receives a new reward and tries next action, and that will lead to next reward. Okay, next state and next reward. Okay. So maybe at this point I should ground it to one example. Let's not be very all over the place. So think of the agent being Roomba. Okay, some cleaning hardware. So the agent's decision is going to be to where to go. Okay, left, right, front, back. Okay, or to just stop or refuel, something like that. A few actions, and there's going to be a reward, which is for its reward maybe just I collect dust. Okay, and the state is going to be just maybe the location where the Roomba is. Okay, so by taking a left action changes my state. Okay, which is that I'm in a new position, right? So action influences my next state. So I'm in a certain position, I take an action, I go to a new state, which is new location. Okay. So I think I'll skip this part. Yeah, I'll skip this part except for, both slides are basically telling one thing, which is that in reinforcement learning, if you want to kind of think of supervised learning that you've seen in the first 7 lectures of this class, supervised learning is all about going from here to here, right? And you have a training signal, which is what is the desired output, what is the desired label, right? Class label. Here, you want to go from input to output. Outputs are actions, decisions, and actions kind of determine what's the next input. Okay, so in supervised learning, kind of assume that if you reorder the data, there's nothing, there's no change. Here, really, data is dependent on what did you do before, right? And the training signal is just rewards. Like, okay, you took an action that gives me a reward. So there's some analogy between these two things, if you want to kind of think of it that way. Any questions up to this point about the basic components? Environment, action, states, and rewards. Okay. So now we're going to focus on how to design that software, how to design an agent who's going to take good actions to maximize that total reward, right? So to do so, we're going to kind of have 3 different objects to play with. So the agent needs to take actions. That's his output, his or her output. So they can, there are 3 objects which are related to taking these actions. The first object is called a policy. It's just a name, okay, which is just a name given to a function. So policy is just a function. Okay, the first one is just a function. I'm going to represent it as pi, which is a mapping from states to actions. Okay, like in situation something, do something. Okay, so that's the first object that the agent will kind of play with. Second object is called a value function, and I'm going to describe in detail what value function is, but at this point I want to motivate it by saying that value function is a function. Okay, it kind of assigns values to states, values to situations, basically. It's basically saying being in this situation is good, being in that situation is bad. Okay, so you have situations, right? A set of situations, a set of states. Value function is just saying, assigning a value to that state, each state. So you're saying being in this state is really good, you can do something, okay, and being in that state is quite bad. Okay, maybe if the Roomba kind of corners itself, it's a bad state, like, literally, right?
So in terms of like reward, as in
Yeah, this function is going to say how good the state is, and the goodness is going to be in terms of what are potential rewards you could have collected, you can collect from the state, essentially. Yeah, high level. We'll actually get to what exactly is definition of this soon. Yeah, but you're correct. It's related to rewards that you can collect from that state onwards, actually. Third object is just a model. So what does agent thinks the environment looks like? If agent knows exactly what the environment looks like, then the problem is actually simpler. Okay, so this point is kind of important. I don't know if I have a slide for this. Okay, so this point is important, which is that model just means what is the model of the environment. Like agent is taking actions in some in a setting in the environment, right? And it's changing states because of its actions. If the agent knows everything about the environment, then it's not called a reinforcement learning problem. Okay, it's just called a planning problem. This is just an aside. I mean, in today's lecture we are just focusing on reinforcement learning, but what I'm saying is, if you know everything about how the world can, move forward for every action that you take, then you know exactly what you need to do. Like if I take this action, I know where it's going to go, and if I take some other action, I know where it's going to go, what's going to happen, how I'm going to change situations. So if I know all that, then I can just solve a pure computation problem to figure out what is the best action to take in each situation. Okay. So in reinforcement learning, the agent doesn't have a good idea about the environment. Okay, the Roomba doesn't have any idea of where it's working, for example. Okay, so reinforcement learning is essentially a trial and error framework, by which I mean, so let me just write it, trial. Trial and error approach. And this is the same idea as even bandits, right? Just think of the bandits. If I knew all the mean rewards, I know precisely. My planning is very simple. I just pick the decision with the highest reward. Okay. The whole point is I don't know what the rewards were for each of the arms. Right? There were 3 arms. I don't know which one gives me how much reward, and that's why I had to do trial and error essentially. But what I was doing was really clever trial and error to maximize my total reward. Okay. So it's the same situation here. I'm just drawing an analogy between bandits and here, in the sense that I don't know exactly how the environment kind of changes situation based on how I act. Okay. Okay. So policy is the first object, and it's kind of related to how the agents can take decisions. So policy is just a map, which just means a function from a state to an action. It's just saying, if you are in state S, take an action little a. Okay. Then I'm going to just call it a deterministic policy, and a stochastic policy is just a slight generalization of this, which is just saying, okay, if you're in state S, okay, you may have a distribution over which actions you want to take. Okay, let's in the Roomba's case, Roomba is in the center of the room, then it will have maybe it has a uniform distribution, as in go north with probability 1/4, go west with probability 1/4, go south with probability 1/4, and go east with probability 1/4, something like that. Okay, that would be a stochastic policy. Then it will flip a coin, 4-directional coin, whatever, sample from that PMF, and take a action. A deterministic policy will say, okay, if you're in this situation, take exactly this action. Okay, and both I'm going to represent it as. So actually, deterministic we're going to represent it as pi. And stochastic, we're going to represent it as like a distribution, conditional distribution, basically condition on the state, do something. There's going to be distribution of actions. Okay. So that's a policy, and whether you plan or whether you do reinforcement learning, the whole point is figuring out the policy, what to do in different situations. Okay. So what is okay? So here is an example. Because I was taking Roomba as an example, but this is a slightly different setting. Let's think of this as a maze. So there's a starting position and a goal, and so what I want to give you kind of as an example is what could be a state here, what could be actions here, and I mean here, this is what is written here: rewards of -1 per time step. Okay. Action is going to be north, east, west, south. So that's right for the Roomba, and state is going to be the location. 2D coordinate. Where is it? And what does black and white mean? White are places where you can actually go if you take an action, and black is where you cannot go. So, and for example, a policy in this example is just what to do in each situation. Maybe in this situation go north. Maybe in this situation go west. Right? Okay. So that's what a policy is. This is just an example, but you can imagine this is just to ground your kind of visual thinking in case if you want to have a grounded example. But this applies to other things like inventory management and so on, other decisions. Okay. This is planning problem. If you knew everything about the maze, if you as an agent knew everything about the maze, you would solve the maze. It's a computational problem. Planning problem is essentially, when I say planning, think of just pure computational problem. Everything is given, input is given, you just process the input and give an output, which is the policy. That's a planning problem. Here, your input and outputs are just specified by what I said before. Your input is a state, you take an action, your output is just a reward. So, it's at a different level. It's not a planning problem. It's a reinforcement learning problem. Okay. So for a planning problem, the input is the whole problem instance. Everything is known. Just tell me what the best policy is, or what actions take in each situation. A reinforcement learning problem is not everything is given, because you are trying different actions, different situations, learning in different situations, and learning from that. Okay? Learning from that to figure out what is the best policy. There's a difference. And we'll come back to this again and again. Yeah. No, this is an example policy. I mean, you could have a policy which is like always go left. Maybe it's a bad policy in terms of reward prediction, right? This is just an example.
If I understand what you're saying is, if we were trying to build, let's say, a Roomba to specifically clean this room, then it would be a planning problem. If you're trying to design a Roomba which would clean in general, then it would be a
No, if the Roomba knows the exactly room design, it can solve the computational problem and figure out what is it. Computational problem is it doesn't have to try any action anywhere. It's just
knows exactly where to go, basically. In which state you are.
It knows because it can solve the computational problem. Okay, I haven't told you how to solve the computational problem. It's not that just because if you tell me exactly this is the maze, I know everything about it, global information, then I can just go back to my home, open the book and figure out all the ways to do it and know the best way, and then tell me this is the best way. Here, the agent doesn't know everything how things are. It will maybe go here, maybe try to go here, hit the wall, maybe go here, go to a dead end, and then realize, okay, this is not the right way to go. It will keep wandering around, okay, collect different rewards, figure out what is the best action taken in each situation. So each is a situation. Here the situations are like next to each other and they have meanings. But in the previous lecture, situations they were like pretty abstract. It's like try this action, this action, this action. There was no the context had nothing to do with each other because they were not related. Here the contexts are related. Remember the contextual boundary setting? The context, user coming to this page, whether they are working professional and are a big MSN fan, had nothing to do with the next user coming to the page. They may be a random surfer who Googled and got to this page. Here, context is this white block. You do something here, you're actually going to the next block. You know exactly, you don't know exactly which context you're going to get to, but you will see that you land somewhere through this stochastic. But contexts have related relation. Yeah. These are the states. So here there is no stochasticity yet. So here, for example, one form of stochasticity could be you take an action north. In this, let's say here, take an action north, but with some probability actually go here because the motor is not working properly. So let's say in Roomba's case, you wanted to go north by 1 feet, but motor is pretty random, or maybe there's some erratic electricity, so you only go half a feet. So you land in a different state, right? If the location is slightly different from what you expect it to be.
Yeah, it could not end up completing the same the whole reinforcement algorithm.
No, the reinforcement learning algorithm, or it's not an algorithm, it's a framework. There are several algorithms there. But they're all trying to figure out what is the best thing to do to maximize total reward. I haven't told you how to solve this yet.
end up in a loop, like not taking the wrong decisions, going to the wrong states all the time, right?
Yeah.
That could be one possibility where you not proceed further.
Yeah. So the agent can end up in a loop. Yeah, that's true. Agent can end up in a situation where they can never return back and collect any reward. Yeah, those things are possible. So that's why I said I think I emphasized this notion of having a simulator, right? I told you cannot really do reinforcement learning. I mean, you can do reinforcement learning in real life, but pretty limited. This is to try different things to see what's better, right? Like how bandits or contextual bandits can work. So here you really need to have access to a simulator. So the agent is really interacting with the simulator, sometimes dying, like in the games, right? In Atari games, the agent must have died several thousand times and learned that okay, I should hit the brake to get more reward.
What does a simulator do?
Simulator is just a simulation of, it tells you where you would land next. It's like a proxy for the real world. It's just telling you, like a car simulator, for example, a traffic simulator would just say, if you take, if you're building an autonomous vehicle and you steer left over here, maybe you'll hit the curb. Okay, that's what the simulator will tell you. You can also do that in the real life, and they may damage your actual hardware. So
you can only do one step forward. What if you realize can the simulator
Yeah.
do like 5 steps forward?
Yeah.
If you take decision now,
Yeah. Simulator is just a full, basically a copy of your real world. So building a simulator is very tough. So a simple thing is like a simulator could be just a game of, like in the game of Go or Atari. Atari already they have a simulator, which is the actual game. So the agent can only control left, right, whatever, shoot buttons there. The game is completely like it's just a piece of software. That's a simulator, and that's the real world for them as well. But for autonomous driving, for example, there are simulators which simulate the environment, simulate how the car will interact with the environment. So there's not just one step. It can be multi-step. Like any video game can also be used as a simulator if you want to. If you think that the physics are realistic. Okay. So let's look at the second component, which is value function. And so value function is a number that you assign with each situation, and it's actually a prediction of future reward. Essentially, how valuable is a state? To quantify how valuable a state is, you just want to say what could be the total future reward you could get if you are in the state only. Okay, so it's kind of forgetting the action aspect, saying you are in the state, do something, you'll get some rewards. We'll get to what you can do, but let's say you fix on a particular policy. In a sense, let's say you remember that there is a particular policy that you want to kind of continue using for every situation. Then it's saying you are in this state and you're going to follow this policy. You're going to hit different states, collect different rewards. The value of the state is the expected total reward that you can get from that state. Okay. Given, for example, if you're following policy 5. Okay. Because 5 is telling you, so you're in state S, right, at time t. Pi tells you take action A. Because you give S to it, it will tell you what action to take. Take that action. You land somewhere and you get a reward. That's the reward here. It could be random, that's why it's an expectation of set. You land somewhere, and there again pi will tell you what action to take, that st plus 1. And because pi will tell you what action to take, you take that action, you get a reward, and you land somewhere, which is st plus 2, and so on. So given a pi, given a policy of how to act in different situations, even if the whole thing is random, you land in different situations. You know exactly, because the policy tells you what to do in each situation. You will keep moving forward and keep collecting rewards. This is just a way to write it. Okay. And we just wrote it as condition non-starting state because things are stochastic. That's why we took an expectation, and so this is a notation. So that's the value given to the current state. Yeah, gammas are discount factors. So these are like I discount rewards in the future compared to now. Okay, like forget about this. So I'm saying that if RT plus 1 is the reward that I get now, and RT plus 2 is the reward I get in the next time step. Then I don't, I value this reward lesser, a little bit lesser. That's the discount factor.
What's the negative?
You don't have to respond if you don't want to. You can maybe even make gamma positive. You value future rewards compared to current reward. But this is a convention, and it aligns with many other things like time value of money. So you value money now compared to money in the future, for example. And also, technical reason is you want the summation to be finite. So if all the rewards are upper bounded by, let's say, 10 units, you only get $10. If it's an infinite sum with gamma is equal to 1, let's say, if it's a sum, then you will have maximally infinity. But if gamma is 0.9, let's say, then this whole sum is going to be upper bounded by some huge number, but fixed. Cannot be infinity. So that's a technical reason. So things don't go to infinity. That's why gamma is there, but there's also realistic motivation. Okay, so here is an example. So for the previous policy, so remember there was a policy I drew in the same example, right? Take a left here, take a east here, I think north, south, east, west for the actions. So these are the values assigned to the states. So this is a state, the white block. So let's think of this. This is a state. The policy tells you go east, right? And the value of the state is the expected reward you can get from that state onwards. Okay, taking an action. So we said every reward at every time step is -1 in this example, right? Where is it? Right. Reward is -1 per time step. So that's why I'm saying, and the policy, let's say this red thing is the policy. Like in every state, this is what you do. In this state, you will not go this way, you will only go this way. Okay. There are some states with 4 actions, right? Like 3 actions here. You could go back, go down, go up, but you'll only go up. Right? So for each state, so this is the policy. For this policy, that is the value function. So these are the different values of different situations. So being in, for example, in this state is quite bad. Like really, if you are in a bad state. And being here is better. Don't worry about the negative terms, just think of this as, maybe this is $100 and here it's $0. Here's my pen, actually. So the third component is the model, and the model is just the dynamics of this system. It just means that how does situation change from one to the other because I took some action. Okay, that's what I want to describe. That's what the environment does, right? So you take an action, you are in some situation, take an action, you get to some other situation or state. So model is basically what the environment will do next, because it's a model, it will tell you what the environment will do next. Okay, and so I'm going to use 2 notations, script P and script R. It's just saying, so what is script P? It's just saying I'm in state S, I took an action little a, where will I land? Okay, there's some probability associated with that. Right? I'm in the situation, I took an action, I land somewhere. So that's a model of how situations change as I take actions. Okay. And remember things from Markov. So my current situation determines where I'll land next, not everything else in the past. And even our script R is a function which just says, okay, we're in some state S, you took an action A. There is some randomness in maybe what the reward you get. Okay. For example, reward can be like Bernoulli, right? Like maybe you made your action probably was some website redesign in some situation, and the rewards that you're getting are Bernoulli. Maybe sometimes people click, sometimes people don't click. So there's going to be some expected reward that you would get, right? So those are these two objects. This object is going to be important. Both are important because that's what determines the objective function. The objective, there was an expectation, right? So that expectation kind of has to take into account this type of randomness. So where do you land next? And also this randomness. Maybe given a particular state, given a certain action, this thing is random. So it has to take both into account. That's the expectation. Yeah, here the minus ones just show the rewards. There's really not much going on here. And the grid layout represents the transition model here. In fact, it's not stochastic. So here, minus ones are rewards. In this state, take any state you take an action, reward is minus one. That's what I wrote. I remember in the example. So in any state, these are all the states, fixed number of states. Reward is always minus one. And the transition is saying, I'm in this state, take a left, I'll go here. If I take in this state, go north, I'll go here, and so on. So transition is quite degenerate here. There's no stochasticity, no randomness here. Pretty much. Okay. Yeah. Any questions at this point? Okay. So we're going to look at this policy, the value function, and the model in the framework of Markov decision processes. Markov just means memoryless, or things only depend on the current situation. So, and in this, why are we bringing in Markov decision process into the picture? To kind of formalize, I had this objective expected total reward or something like that. We're gonna explicitly look at a, kind of ground it further in terms of preciseness. And then our objective is to maximize over all policies the best policy. Okay. So you want to maximize that objective, expected reward, total reward, and we get to choose policies, which means different pies. Different pies means different actions in different situations. That's I want to get the best policy. Okay. So we'll start. This slide is just saying we'll start with a Markov chain. To understand the Markov decision process, we'll start with the Markov chain. Try to understand what is the Markov reward process, and then try to understand what is the Markov decision process. They're all related in the sense of, on a Markov chain, you add some additional information that becomes a reward process, and on top of that, you add decisions, it becomes Markov decision process. So we'll see. This is a natural progression. Okay. So, but Markov chains are also essential because they are things that you saw in forgive sampling. Okay. So in Markov chains, what you define, what the kind of key object, if you remember, there was a q function that I was saying, q of x prime, x to x prime, like something like, remember, q of x to x prime, right, in the Gibbs sampling in the Markov chain Monte Carlo methods. So that is the same thing as what's written here. It's a conditional probability. Conditional probability of being in some state and going to some other state. Okay? That's this q function that previous two lectures, and it's p of script p s prime here. Okay, so you can think of it as actually just a table. It's just saying if you're in this state, going to some other state, there's some probability number associated with it. Okay, assuming there are n states, and so this is an example where I guess the blobs represent states, and arrows represent transitions between different states. And that's it. That's a Markov chain. The transition probabilities are given on the arrows. Okay. For example, being in a state and exiting the state has total some probability 1. 0.6 plus 0.4, right? Sum to 1. That's an example of a Markov chain. Any questions at this point? So these are just, so for us it's, Markov chain essentially represents transition from state to state. For us, it's basically transition from situation to situation. So, let's say you started from some starting point, let's say class 1, C1, and you ran this chain, as in you jump from one state to the other according to the transition probability. Then you may get some sequences. These are called episodes. Maybe there's a sequence where there's a state where there's no outgoing transition. So there you just stop. There's no further sequence. Or maybe you don't get to the state, you keep going on. For example. So these are actually going on till you get to it. So these are called episodes. Just a name for this. Or you can always say I'm only going to run the Markov chain for 3 steps, and the episodes are going to be just this, and this. Okay. That you specify. And this is the specific, the numbers there just represent the matrix here with where there are no numbers are zeros. Okay. That's a transition probability matrix. Okay, that's Markov chain. So that was very quick dealing with Markov chain, but that's the same component that you'll see in Git sampling. Now let's get to a more interesting part, which is the Markov reward process. And Markov reward process is essentially a Markov chain with some additional numbers, and that means the additional numbers are basically specified by these last two lines. So let's say script S is a set of states, okay, set of situations. Script P is the transition probability matrix, essentially going from how do you go from, like, if you are in this state, this is all the probabilities of going to other states. Okay. The additional information for a Markov reward process is going to be just a reward function, which is going to be, for example, what is the expected reward that I get at state S. Okay. So this is just a reward. So this is slightly different from our rewards. We'll see our rewards in our reinforcement learning setting, but you can think of assigning numbers. Basically, if I'm in this state, there's some random number that I can generate, and the expected random number is going to be this reward function. And gamma is a discount factor. Well, that's not very important at this point. That's it. That's those. So basically, I'm assigning some randomness at every node, every state, essentially. Random number at every node. Okay. So that's a reward process. So why the name? Because if I run the Markov chain, then I get some bunch of rewards. Then I can add them up and say, this is the reward I got. Right? So before that, let me just define another quantity, which is going to be a sum of rewards. It's called a return. Okay. I'm going to use the notation GT to represent return. And GT is just going to be a sum of bunch of random variables. Okay. See, in the Markov chain, I'm a state C, C1. Remember this one? Actually, there's an example right afterwards as well, maybe. But there is a class 1, C1. I'm here, then I don't really have to take any action. I'm here, I jump to another state because there's a point where probably I go here, a point where probably I go to Facebook, right? There are only 2 outcomes. So I'll definitely flip a coin, pick one of these and go. So there's no actions involved here. Because I was here, I'll get a number. That's the reward. So I keep going around this according to the transition probability matrix, and I keep collecting the numbers. That's it. Those rewards. Okay. So the sum of those rewards, maybe you stop, maybe you don't stop. So for simplicity, we just assume that you don't stop, and there's a discount factor so that the summation is constant. And I was just telling somebody in the break that if you had a bunch of numbers and maximum reward is, let's say, 10 units, then because this gamma, the discount factor is less than 1, so you will not get an infinite summation. Even if you do, even if there are a lot of terms here, your total sum is going to be quite bounded. Okay. It's not going to blow up. Okay. Yeah.
So in here, we are not making any choice.
At this point, this is just a motivation from, there was a simple thing which was Markov chain. We just added numbers, stochastic numbers to each state. That's all the Markov reward process. I'm just defining a return. Next we'll add decisions into the picture. Yeah, and that's the object we care about. So because even at this level we can talk about value function. Okay? Here there is no actions, but there is a value function because I start at some starting state of Markov chain. I keep jumping around states. There's no, I don't have to explicitly pick an action. I just keep jumping around from situation to situation. So I keep collecting rewards. So there's a value I can associate of being in any state. Okay. Because if I was in this state, I start the Markov chain from there, I keep jumping around and get some rewards. And whatever. Starting from that state, I'll get a bunch of rewards. The value function is just going to be the expected return or expected total reward. This is the total reward, and I'm calling it return. The expected return that I get starting from status. It's a number that I can assign to each state. Okay, in that Markov reward process or Markov chain. When these are called process because of some reason. But any confusion, any clarification? Oh, so in this setting also you can define what a value function is. Value function is just the expected return. So these are all random, right? These are random numbers. In fact, what's hidden here is that where you land next is random because of Markov chain. Which state you land, and on that state, what is the reward that you get? Some number associated with that state. That's random. So overall, this whole thing is random. So that's why there's an expectation that I can take. I just choose to take an expectation of this return. And this expected return value starting from status is defined to be the value of that state. Okay. It's basically saying what is the discounted total rewards I can get from this state versus discounted total rewards that I can get from some other state. Because I'm not controlling actions anyway, but I'll collect something. And so there's intrinsic quality of B starting from this state versus that state versus that state. So for us now, really, we have kind of abstracted out, and we are not calling situations or contexts and so on. We are just really thinking in terms of the state space. Bunch of states. We're going to jump around states. Okay. It's an example, but let's not parse it now. It's just a computation of those, the return value G. Okay. With some parameter, let's say state 1 is the class 1. There's the transition probability matrix that you saw, and gamma is 1/2. So for that, they have just computed what these numbers are. Okay, the value of being in the state. So like for example, these are the different episodes. So from class 1, I did something in this because they're from Markov chain. From class 1, again I did something else because of randomness. This one episode, this one episode. For each episode, I can say, okay, I collected some bunch of rewards being in each state. -2, -2, -2, 10. And there's some gamma square, gamma cube. Right? So this is the value in one episode, this is the value in another episode, this is the value in another episode. So expectation will be just average of these numbers. Okay, average of these numbers. Yeah, and there's another interesting property, and this is where maybe some people who have seen dynamic programming may be able to relate, is that this value function can be decomposed into two parts. One is the immediate reward, and there's going to be a discounted value of successive state. Okay, successive state, which is gamma times value of the next random state. Okay, and that you can see here. Value of a state is just the expected return that I get from that state. Next, I'm just substituting the definition of expected, substituting the definition of the return, right? And then I'm saying, okay, I can take gamma common here for this part, right? And then this part is just the return from time step t plus 1 onwards, right? Because it's an infinite sum. And then I just move the expectation. So this is random variable, this is a random variable. This is a random variable which involves a bunch of lot of random variables. But I can think of this expectation, since this expectation, all these expectations were over all the randomness, I can split that expectation into current randomness, which is this and the state, and all other randomness I can take an expectation for. Okay, that's just B. Okay. So So okay, from this step to this step, what I'm saying is instead of G, I replace it with B. So B of a state is the expectation of this guy. So where did the expectation come from? I just pulled the partial expectation from here. So okay, that was a very bad way to say that. So it's basically, see, let me write the expectation properly. So it's expectation. So what is this expectation? Let me just write one step. So it's expectation over the probability of going to st plus 1 given st. There's that randomness. Okay. There's also an expectation with respect to reward rt plus 1. Remember there was this reward was random, right? So I'm going to subscript with the random variables. So there's going to be an expectation with respect to probability of st plus 2 given st plus 1, right? There's a randomness there. There's going to be a randomness with respect to rt plus 2 and so on, right? So this is this expectation here, because it has to be expectation over all random variables into my argument, which is this gt, right? So that involves this random variable, this random variable, this random variable, this random variable, right? All I'm saying is, from this step to this step, I'm just saying that I'm gonna make this guy, this E here, just be these two, right? So this expectation, so the starting expectation is this whole sequence of lot of expectations one after the other. At this step, all I'm saying is I'm gonna push some of these expectations inside, because this doesn't depend on this rt plus 1. There's no rt plus 1 from here onwards. So I can push that E inside. Same thing with P of st plus 2 given st plus 1. I mean, it's gonna, st plus 1 is known at this point. So this point onwards is the expectation here, which is precisely the definition of value function. Value of all the rewards I can get starting from state st plus 1. Okay. So say st plus 1 is itself random, that's why it's capital, and that therefore there's an expectation, because st plus 1 is random. This expectation will take care of that. Is that clear? If it's not clear, ask me. Clarity is more important than covering material. Yeah. How did I replace instead of gt plus 1 b of st plus 1? What is v of little st plus 1? V of little st plus 1 is the expectation of g of t plus 1, right? Given I don't know, st, actually st plus 1 is equal to little st plus 1, right? There's an expectation or something, right? What I'm saying is that expectation of something is these guys. The original expectation is actually expectation of all random variables. Random variables are st plus 1, rt plus 1, st plus 2, rt plus 2, st plus 3, rt plus 3, and so on. All those random variables, the expectation is this short form E. Now all I'm saying is the same E comes up to this point. Okay, I'm gonna now kind of, this E is a bunch of expectations, integration or summations, just think of some summations. I can push some summations inside, because except for rt plus 1 and st plus 1, everything else is nothing to do with rt plus 1. Nothing to do with rt plus 1. Because there's no rt plus 1 here, now rt plus 1 here, no rt plus 1. So I can push it past rt plus 1, right? So I'm making an expectation of this guy. Essentially, when I push remaining expectations here, I'm making an expectation over this guy, because rt plus 1 is missing for these guys. So these guys just take an expectation over this guy. These guys take an expectation of this guy. So that is what this is. This square bracket I showed you is just this. Any other question? Okay, so why did we okay, why are we looking at this, this interesting property of value function? Okay, I should say that right here, is that will give us clues on how to learn policy. Ultimately, what we are doing here, at this point, it's not clear how this is going to help us learn policies in reinforcement learning, because this, first of all, is it's a reward process. It's a Markov chain with some numbers on top of it. But ultimately, this type of form you'll see again and again, and it's kind of gives our first algorithm, which is called Q learning. Okay. So this recursive form, so the value of a state is the expected reward, expectation of the reward it can get, and go to some other state, and the value of that state, discounted value of that state. We saw the derivation in the previous slide. Starting from the current state. This is the recursive definition where V appears twice. Okay. So the expected reward, we use the notation RS, script RS in Markov reward process. And the expectation of this value function, we can write it explicitly this way. Gamma is a constant. That expectation is a summation. Right? Summation of all the next states I can get to from the current state. That's all the next states I can get to and the value of the next states. So this is the recursive equation. V of S is related to V of S primes, or a bunch of different S primes that I can get to from this state. This picture is just saying V of S is related to V of S prime. These are states. Okay. So let's not worry about this picture. We'll see a different picture and then I'll explain. So this is just the same thing. This recursive equation is slightly less notation or slightly different notation. It's the same equations. So with that, let's get to Markov decision process, where now we are going to introduce the key ingredient, which is actions, decisions. Okay. So Markov decision process is just a Markov reward process with decisions. And so previously I had states, transition probabilities, reward function, and some discount factor. I'm going to add a bunch of actions, right? Script A is a set of actions, the one in red, and make the transition probability a function of the action. Okay, so which next situation and which next state I get to depends on the current state and the action I take. Okay, so in every situation, in the previous settings, Markov reward process, Markov chain, in every situation, you by default are jumping to something else just by transition probability. Here, in a situation, you have to pick an action. Based on an action, you know where it will go. Okay, so it's action dependent transition to potentially new states, potentially different states, next situations. Okay, that's all. So that's the minus change. And similarly with the reward. Reward is now just not a number associated with the state. It's a number associated with the state and the action that you took. Okay. Yeah. So here it's a slightly different problem. I guess it's an example NDT where the red things are now actions. So think of these as not. Think of these as circles and squares as states, and the red things as actions. And actions make you go deterministically from one state to the other in this example. Actually, no. There is is that a state? So the outgoing probability, okay, sum to 1, okay. Oh, okay. Okay, maybe in this state there is no action. You just jump to class 1, class 2 or class 3 after going to the power. So reds are actions. Some are deterministic in the sense if you are in class 1, take study, you will definitely go here. There is no other stochasticity. There is no transition. The transition probability is 1. You go to next state. Here there is no action in the sense because basically there is no actions to take. You by default jump to something or the other. Okay. And that's it. That's the mark addition process. Yeah. So there is stochastic. So yeah, with some probability line this way. So yeah, this part is stochastic. Remaining parts are unfortunately not stochastic in this example. So there is no expectation there. But basically, the summation is gone. Just one particular specific transition based on this graph. Okay. So I've already defined what a policy is. Policy is, in general case, policy is the distribution of our actions given a state. Okay. So that's the ingredient that we had discussed before. So okay, so why did I introduce policy? We have an MDP, which is basically this 5 things: states, actions, transitions, rewards, and this discount, and a policy pi. This transitions and discounts are the model aspect of the problem. So this is where the dynamics of the environment is captured, right? Like how do I go from one situation to the other? How does environment go from one situation to the other? How does the state of the world change from one situation to the other? Okay, you get to only control actions, and you get to control actions. You see states. Okay. So let's say you fix a policy pi. In the sense, if this is a state, you have to do Facebook. If this is a state, you have to do study. Okay, or some fixed actions. Somebody is telling you this precisely what you need to do. Then, if you fix the policy, then the sequence of states is a Markov chain essentially. Once I fix the policy, then again I don't have any control. Like in the state, exactly it tells you what the action it is, and if you know exactly what the action it is, then you know exactly with some stochasticity where you will go. Okay, so you don't have any control. So it's actually a Markov chain. It becomes a Markov chain if you fix a policy. Okay, and if you fix the policy, you will get rewards as well, because R was A was not in your control, so you will still get rewards, and so essentially you'll also come back to a Markov reward process. So fixing a policy, state transitions happen like a Markov chain. Reward numbers get like a Markov reward process. That's all. And like what is this? Okay, this we are assuming a stochastic process. So stochastic policy here. That's why there's summation. So let's not worry about this stuff actually. Yeah. So let's not worry about that. We'll get it will not come up next. If it comes up, I'll just describe what it is. Okay. So now in Markov decision processes, let's talk about value function. In Markov reward process, we define value function. This is just the given a state, collect a bunch of rewards. What's the expected total reward I get, right? In Markov decision process, we're going to define what is called the state value function, which is going to be V pi of S. Okay, which is the same as basically Markov reward process. When I have fixed the policy pi, like if I fix the policy pi, it's a Markov reward process. I don't have any control. I go from one state to the other. There's a number being generated because policy pi pretty much says if you're in state S, take this action, and if I take that action, I know exactly what rewards I get. So I don't have any control. Fixing a policy pi is essentially a Markov reward process, and we just define what it is. It was just expected return starting from state S. Subscript pi is because I have fixed the policy pi. What to do in each situation. Okay, that's the only new thing that I've added. Okay. So I'm going to call that state value function. I mean that was basically the value function from before. I'm just going to call it state value function. That's because I have a different value function to define, which is the action value function. Okay, this is a new object. This object is saying it's slightly different. Kind of pay attention here. It's saying what is the expected return that I will get if I'm in state S, okay, starting from state S, taking an action A, and then applying my default policy, so applying a policy pi, okay, is letting me choose the first action. So I'm in state S, little s, okay, at st is little s. I get to choose some action, but after that, is basically a Markov reward process because pi is fixed. Okay. So that's called an action value function because now I get to choose an action at the beginning.
This simple example that you told, the arrow marks left, right?
Yeah.
There will be 3 arrow marks and you get to choose one of the actions from it. Can you relate that one with this?
Yeah, you can. Yeah, so it's basically the value of being in some state and taking action. Here it's just the value of the state only. Okay. You can compute these numbers for that example as well, but I have computed these numbers for that example and I plugged it into the white box. Each white box was a state. So I had plugged these numbers, I plugged these numbers in that example. I didn't compute this there, but this can also be computed for that.
Is this only for the starting state? Like you were to pick an action only the first?
Yeah, you get to pick only actions on the start.
And the rest is.
That's is followed by pi, right? So somebody gave you the pi. So what will you do? I mean, you have to use the pi at some point. So you use it from next state onwards. Okay, how are we doing with time? Okay. So why did I introduce that state action value function? And why did I use the value Q? Is because it's going to be related to something called Q learning, which is the last part of this lecture, which is the learning algorithm, kind of very important baseline for reinforcement learning. So remember, goal of reinforcement learning is to trial and error, figure out the best policy, what to do in every situation. What to do in every situation is basically pi policy, and the policy, whatever you reinforcement learning through trial and error figures out, should be the one which maximizes the expected total reward. Right? That's always the goal. Okay. So just like, so this we saw, like condition on pi is a regular value function, so we knew the recursive relationship. Recursive as in like v pi of s is related to v pi of st plus 1. Right? V pi of at st basically is related to v pi of st plus 1. That we just saw. Similarly, the action value function can also be decomposed. The q pi of st, a is related to q pi of st plus 1, at plus 1. It's kind of the same relationship because it's basically the infinite sum. You just look at the second part of the infinite sum and it's the new q. Okay, the expectation argument that I was giving, right? I mean, this, at least by analogy, you can see that it's basically very similar. Okay. Okay. And like really to write. Okay. So just to kind of couple of tangential points or couple of just remarks. What I wrote in the previous slide is again repeated here, but I've slightly used a slightly different notation, which is that I'm saying that the expected reward of being in state and taking action A is this. That's our expectation by dropped out, plus gamma, and there was this q pi of s comma st plus 1 comma at plus 1. I'm saying in starting from state S, taking action A, there will be some probability you will reach S prime, and from S prime you will take some action A prime. There's a q pi of S prime A prime here. It's the same expectation equation, it's the same equation that we saw on the previous slide with very different notation. Okay. This summation may not be there if the policy is deterministic, by the way. If the policy is saying if you're an S prime, take a specific action A prime, then this is not going to be, summation is not going to be there. Okay. And this is pictorially represented here. You are at S comma A, okay, which is the black dot. You could randomly go to some state S prime. Okay. And that state S prime, you can take actions A prime. Okay. So q pi of S prime A prime involves both going to some state randomly and taking action, which could be random. That's why there's two cups here. But so this picture is just showing like this guy q pi of S comma A is related to q pi of S prime A prime. That's all it's saying. So this picture is just trying to show. I mean, it's drawing a node for it's drawing a node for S comma A, let's say, or let's say it's S comma A. It's saying from S comma A go to some state S prime, and again go to S prime A prime. So two levels, and this guy, the thing related to this black node, is also related to the thing related to another black node through this equation. The left hand side is related to many of these guys. That's all. That's a pictorial representation. This may not be very useful, but this is very useful. And this is called the Bellman expectation equation. So Bellman is a famous scientist. So he solved a lot of preliminary seminal works in dynamic programming and Markov addition processes. So this is called the Bellman expectation equation. So let's come back to the objective. So in Markov addition process, because now we have actions, our objective is to find that policy that maximizes v pi of s. This is a state value function given a policy. I want to search for the best policy. That will give me the highest state value function. State value function, highest state value function, or this state value function is what we want to optimize for. Remember, I said total expected reward. That is what state value function is, starting from some state s. So we are searching for policies pi. And let's say there is a pi which maximizes these numbers or all policy pi's, so all policies, and let's say that is v star of x, v star of s. There is a number, right? So if you are maximizing something, there will be a number which attains that maximum. The maximum attains some number, right? Let me just call it v star of s. Okay. And similarly, I'll call this number which maximizes the state action value function. Right? I fix the starting state, fix the starting action, and then I'm using a policy. I get for every policy, I'll get some numbers like this. I want to pick the policy which has the highest number, and that number I'm calling it q star of s for. Right? Okay. So v star of s comma a and q star of s comma a also satisfy some recursive equation, which will not show here why they satisfy that equation. It's called Bellman optimality equation. The previous one is Bellman expectation equation that we kind of are pretty clear about how it came about. Bellman optimality equation is saying that q star of s comma a is related to q star of s prime a prime. Okay. There is a max operation here. Okay. So this is the best value. There is a policy which is maximizing q star of there is a policy which is maximizing the expected reward starting from state s and by taking action a, right? There is some policy. There is a policy which also does that for starting from state s prime and taking action a prime, right? These numbers are related to each other. Okay, that's a non-trivial part called Bellman optimality equation, and this is what is related to dynamic programming in computer science. If somebody knows it. So it's the same equation, except what changes is these are q stars. It does not depend on any specific policy. These are the best policy, and you have a max over a prime here. Max over the next state, best action in the next state. So that's called Bellman optimality equation. Any questions at this point? Like, we'll get to gradient descent next time when we combine reinforcement learning with neural networks. Here it's not going to be gradient descent, but it's going to be some similar update rule for learning. Here I have not even here. So I've just introduced at this point what are Markov addition process starting from Markov chain. I've said okay, this is the objective, and the value function and the state action value function satisfy these equations. That's all. The story has progressed only up to that point. Now we will get to RL in the next few slides. Okay. I mean, first of all, connect this to RL and then get an RL algorithm. Okay. So why do we care about let's say q star s comma a or v star of s, right? I mean, these are the values, right? Maximum values, not the not the policy. I mean, these are the best values, right? You can actually backtrack what the best policy is if you knew the values. That's just a way to say that if you knew q star of s comma a, then the best action, the policy should just be take the action that maximizes q star of s comma a. If you knew q star of s comma a, if you knew these numbers, then in a given state you'll have one number per action. Take that action which has the highest number. Okay. That's the best policy. Okay. So there's a relation between q star of s comma a and the policy, best policy. Okay. So if you could somehow get a handle or solve for q star of s comma a, then you would get best policy. And the hint is right here, right? So how do you get q star of s comma a for a problem? The problem, what does the problem say? The problem specifies the transition probabilities. The problem specifies the rewards, right? The problem specifies the discount. The problem specifies the actions that you can take, right? A's in general, and the problem also specifies states. Okay. Problem completely specifies everything. Only thing it doesn't specify is what is the best policy, right? In the sense the MDP problem, MDP instance. So given the problem specs, right? These guys especially in gamma, you can actually solve for q star of s prime comma a prime by solving these equations. Find q star of s comma a and many such guys for different arguments, the function, such that this equation holds for that function. If you can find such a function, then you're done. That function, if you knew that function, then you can just take an argmax that I showed you here. If you knew this guy, then you can just get the best policy. That's it. So that's it's a little bit roundabout route of finding the best policy, but so this is a way to find best policy if everything is specified. So this is an example of a planning problem. Okay. So if somebody specifies an MDP to you, which is to say they specify how the transitions happen, how the rewards happen. So all you have to do is find the best policy. That's a pure computation problem. You solve those equations, Bellman optimality equations, for example, get q star of s comma a for every s comma a, and then just the policy is just the one which for every s which a maximizes this numbers is the policy. Okay. So that's the planning problem. Okay. Of course, even the planning problem is hard. Here are just hard because there are too many states, too many actions, and there are so many policies to search for. I mean, in the sense that there are too many states, too many actions. Computing these numbers is computationally hard. Okay. Takes a lot of time. So planning is also quite involved. Okay. But now we are not in the planning realm. We are in the reinforcement learning realm, right? Which means that we don't know how the rewards are going to be at all. In the environment, we don't even know what rewards we're going to get. We have to really do trial and error. We have to try some action and see that we get burnt or we get tons of money, right? So that's why we need a simulator. Okay. So we do trial and error, get an idea of what are the rewards in different states, how am I going to transition from states to states. You get exposed to that by trying out. Okay. And you remember those information or some summary statistics, and so that you can get the best policy after a long time. Okay, that's the reinforcement learning problem. Okay, so to find the best policy in the reinforcement learning setting, okay, now nobody tells you what the transition probabilities are, nobody tells you what the rewards are. So you as an algorithm, as an agent, nobody tells you what the P and script R or script P is. You have to you've been given a simulator though, or even the real world. You can only take actions and observe rewards. That's it. Okay. So to be able to compute the best policy, you need to be able to do two things. Okay. One is you want to do something called prediction, which is which is basically this. Given a policy, you should be able to say how good the policy is. Okay. It just means that if somebody, if currently I think this policy is good, then you should be able to at least tell me what is that score for this policy. You're trying to guess the best policy. So if this score for this policy is the highest, then this is the best policy. So you should know something about this policy, right? So you should be able to compute the score, okay, which essentially is the score. Let's say you are always starting from some state small s, okay. Then to know the score, you need to know q pi of s comma a for every a in that state. That's like the score for that policy, right? I mean, for a state action value function, you'll not have a single score, one score per current action that you take, right? You're starting from state S, you take some current action little a, and then afterwards you're going to apply this policy, so you need to know that score. And if you can know the scores, you need to make improvement over the policy. Let's say I have a current policy, pi 1, the score is 100 units, okay. Then I should be able to like improve it to get to pi 2, some gradient update for example, so that I can get maybe 200 units or 150 units, right? I have to do some improvement, push it, right? And there are many algorithms which actually which actually clearly do prediction, where it's obvious that it's actually computing a score for a given policy, and then they explicitly do update, okay, how to go from a pi 1 to pi 2. But because of lack of time, I'm only gonna show one algorithm called Q-learning, which fortunately mixes those two steps, and so it's not very clear whether it's doing prediction or control, but we'll see. So we'll look at one algorithm which tries to get the best policy, okay. It does both prediction and control simultaneously. But if you didn't really, we're gonna think about from scratch, this is a very principled way to think about it. Like for every policy, if I can get a score, then maybe I can move from one policy to the other, do some update, like move from one current candidate policy to a better policy, something like that. Okay. So what is going to be the Q-learning algorithm? So let me draw this picture where white nodes represent states. Okay, white nodes represent states. Black nodes represent states comma actions, or states comma actions, let's say. Okay. I mean, whatever the previous state is, just remember that, and then whatever action you took. So let's say you knew this guy and R, okay, which is S comma A. Yeah, there were two objects, right? For every state, which state do I land next, given the current state and the action, and given the current state and the action, what is the mean reward? Okay. Let's say you knew this, then essentially it's a planning problem. Remember, right? If you knew this, you would just see how everything goes, right? In a given state ST, you'll say, okay, maybe there are only two actions to take. Then I'll take action A1, action A2. Okay, those are these two dots. From those two dots, because I took action with that state, maybe I can go to two different states in this listed example. Here also I'm going to two different states. Okay, and from there again, maybe there are only two actions. We have to think of two actions. Maybe because of that state and that action, I went to a terminal state. Maybe because of that state and that action, I went to a terminal state, or with some probability I went to some other state, and so on. Okay. Actually, I'm thinking of all the things that can happen in the future. That's because this is a planning problem, right? I know these. With some probability, I'll be here. With some probability, I'll be here. With some probability, I'll be here. With some probability, I'll be here, and so on. Right? And we saw that the Bellman optimality equation said, so there was a little q of s comma a, or actually little q star of s comma a, was equal to expectation of immediate reward plus gamma times max over actions of little q star of s prime comma a prime. That was the expression for Bellman optimality equation. Okay. So now what we're going to do is make that optimality equation into a iterative update equation, which is as follows. We'll start with some numbers for q of s comma a. In the sense, remember what is q of s comma a? It's a number for every state and every action. So think of it as like a table. Okay, for every state, for every action, there's a number. Maybe 10. Maybe action a1 is 10. Maybe action a2 there's a 12. Okay, right? For every state, for every action, there's a number. Right? So start with some numbers for the q. I'm going to describe an iterative algorithm. Start with some numbers. Okay. And then you compute this because I have these numbers. Okay. I have the model. I can compute this expression. Right? And then set that to be the new numbers. Again, start with these numbers, compute the right hand side, set them to the new numbers, and so on. What are we trying to find? We're trying to find q, little q star. Remember Bellman optimality equation, little q star. This is an iterative algorithm which will start from arbitrary numbers. If you do keep updating, compute the right hand side, set it to the q, compute the right hand side, set it to the q. Q is reused, right? Remember? Ultimately, this capital Q will be equal to q star. Okay. And once I've solved q star, I can get the optimal policy. Okay, and this is in the planning version of the problem. Right? But in the reinforcement learning version of the problem, where I don't know script P S prime A and script R S A. Okay. So best way to explain this. Okay, actually, let's directly get to the next slide because this is in just value function space, and I want to keep ourselves in just the state action value space. Okay, because that's where the flow is correct. This is value function space. Okay, let's in a sense. Okay, coming back here, I'm just saying that if you knew the transition dynamics, if you're in the planning problem, you just do an iterative update. Start with arbitrary numbers. You can compute this because this expectation involves basically these guys. Okay, this red blob is just saying expectation, because if you're an ST plus 1 can be only these 4 values. That's why there's a red blob. Just saying that if you are in state S, you can only go to S prime, which are these 4 things. So the expectation is over that red region of the Q values of these guys. That's it. That's why there's a red blob there. So let's skip this slide. Okay. Oh, okay. Here again, I'm repeating the same thing. If you know the model, then you have the Bellman optimality equation into an iterative update by computing the right hand side and setting it to the left hand side, and ultimately, okay. So in this diagram, I'm just saying this was the optimality equation. I'm just going to replace this equal to with directionality, saying I'm going to compute this first, update on the right hand side, compute this again, update on the right hand side, and also. So that's what I'll do with if I knew the model, right? If I knew the model, and this algorithm is called value iteration, just a tangent, but this value is algorithm for planning, as in solving given an MDP, which means given the model script P script R, solving for the best policy is a planning problem, and the algorithm is called value iteration, and it's basically this: start with some arbitrary numbers. I mean, I think we saw it in two slides ago. and keep updating, okay, recursively update. That's called value creation. That's a way to computationally solve for the best policy in the planning problem. Now, if we do not know the model, what do? That's the crux, right? So, what are we going to do is that we're going to take inspiration from the planning problem, and because we don't have the model, we need to have a simulator. Somehow we need to somebody has to tell us what's the next state if I take an action, right? So we're going to do sampling in the sense we don't really do sampling as in the give sampling sense. We're just going to try an action. The environment is going to give us a single next state st plus 1, okay? And with that single st plus 1, you're going to do an update. So we don't have this object. This object is not there. So we only know how to go from st is equal to s to some other state st plus 1, okay? In the sense, from here I can go to either this side or this side. I don't want to put circles there, okay? So I don't have this model, so I'm gonna just get the next state, okay? Let me come back to the second point in the next slide. I'll only get one state, okay? Which means that I'm in s comma a. I get I took some action. I get a reward and a next state, okay? I'm going to specify how to take that action. That's precisely what I've not told you, right? Because it's a reinforcement learning setting. I have to decide what actions to take to maximize expected reward. I'll get to some next state s prime. Think of from s prime also I can take another action a prime, because both were needed, right? In the q value function iteration, it was not just the s prime, but also from s prime what was the a prime. There was a max operation in the Bellman optimality equation, and there was a expectation in the Bellman expectation equation. But you need to know what the next a prime or what the next state. From the next state, what is the next action to be? Okay, let's call it a prime. Okay, and I'm gonna kind of motivate this type of an iterative update, which is gonna be start with some numbers. Okay, start with some numbers, and you update the number in the sense, let's say the starting number is 1. Keep the number 1, or actually this is equivalent to, let me write it in a more interpretable way. This is equal to 1 minus alpha times q of s comma a plus alpha times r plus gamma q of s prime comma a prime. What I'm saying is, you start with some numbers, take a moving average. Let's say alpha is 0.5. So 50%, one half of the previous number that you know in the table, plus one half times the new number that you got because you took an action. Sorry, new R reward that you got because you took an action, discount. Plus in the table there is a, in the table look up where what the Q value was for the new state that you landed in and the new action that you were planning to take. So this is the, there was a summation over transition dynamics in the previous slide when you knew the model. All I'm saying is, if you don't know the model, you just have to take one sample, which is just one without the expectation here, basically. And that I'm saying I'm going to do a moving average, which is that I remember the previous value, I slightly change it with the new information that I got, which is the new reward and this Q of s prime comma a prime. Okay. So that's the motivation for going from value iteration type of a thing to something where I don't have the model. So I'm going to sample, I'm going to try an action, get a single reward or number, and I'm going to do an update like this. So I'm going to update what? The location, the Q value of the state in which I took a particular action. Okay, but I haven't told you how to take the actions yet, and I don't know if I have a slide for that. I should. Yeah, now I'm going to discuss how to take the action as well as what is this a prime. A prime is like in the next state, what is the action that I'm supposed to take, right? So before I get to how to take the current action, I'm gonna even do a modification with a prime. So this is the same equation as before. Okay, the moving average thing. You just see that 1 minus alpha times previous value plus alpha times new value with a single action that it took. So I'll do one more modification to get to Q learning, which is that this a prime, I'm going to change. Remember Bellman's optimality equation had a max here, max over a primes. I'm just precisely taking a particular action. So I'm gonna essentially substitute a max over a prime here. Okay. So that's the change that I did. Two changes. So I started with value iteration, as in the full information case, as in if I know the model, how am I going to do find the best policy by computing Q stars. Here I'm saying I don't know the model, which is transition probability and rewards. So I'm going to just take an action A, land up in some state S prime, and in that S prime, ideally, in the first step of the iteration, I said if I know S prime and A prime, I said let's do a moving average. Here I'm saying let's not worry about A prime. Let's just look at the table of what is the maximum value from S prime, and just substitute that number here. So my current action has led me to a reward R and the next state S prime. Beyond that, I'm just looking at my tables to update my table, the S comma A table or matrix, with the updated numbers through this equation. Okay. So pictorially is just saying that you start from S comma A, which is this, right? You took an action, got a reward, that's the number, spit out by the environment as a simulator. You went to some S prime, state S prime, that also environment tells you, right? From this point onwards, you are taking a maximum of whatever actions you are possible by looking up your Q values. I mean, this is just a kind of very illustrative way of saying that these are 3 actions possible in the state S prime. This arc is just saying take the max over there. Okay. So if you're not interested in the figure, it's just saying this is the update equation I'm going to follow. Okay. So that was the 2 changes that I did, right? So, okay. So let's come back to the principal leftover point. Is how do I take actions, right? I just told you an update. If I take an action A, I'm going to update it like this. Okay, to update my Q values, just like I was doing in the value iteration setting or the full information setting. Yeah. This is just a different way of writing. This is just a moving average, right? This is Q of S comma A times 1 minus alpha. This number is the same as this number. So 1 minus A times previous value plus 1 minus alpha times previous value plus alpha times some new information. That's it. It's not that's just, they just wrote it, did not want to write alpha twice, I guess. Actually, there's another motivation. This is called temporal difference error, but let's not worry about it. Okay. There's a lot of other algorithms which people have figured out. A lot of other algorithms, unified the framework, cleaned up things. So that's why this way of writing it. But further study in that book. There's a book, Introduction to Reinforcement Learning. It's a textbook for this course. So have a look at it. First 2-3 chapters, just to get a feel for this. Okay, so I was trying to figure out. What I didn't tell you is how do I choose A, right? I told you if you choose A, update it this way, and keep choosing A. Maybe keep choosing different A's. Maybe you'll update it, and hopefully you'll get the Q of A. But it's critical how you choose A, right? If I keep choosing A, actually, the best, one of the ideas is to keep choosing A randomly. Okay. In every state, flip a coin. Whatever available actions are there, keep randomly pick, and you will. It works actually. It works in the sense you will figure out Q of S comma A, Um, I mean, in the sense you figure out q, little q star of s comma n, the best q state action value function. But that's not good enough algorithm. So we're gonna decide how to choose actions very similar to the epsilon greedy approach. Remember, there was an epsilon greedy approach in bandits where you said I may have estimates of, let's say, 3 arms. With some epsilon probability, I'm just gonna pick the arm with the highest value, as in highest mean reward estimate. And with 1 minus epsilon probability, I'll flip a coin and pick a random action. Remember epsilon greedy? So here we're gonna do the same thing. We're gonna say, okay, let's say at any given time, I know some QSA values. I'll do 2 things. With epsilon probability, I'm gonna choose the max over Q of s comma n, because that was, remember, if I knew the true values, the best policy is the max over Q of s comma n or all A. Remember, the best policy was related to the best Q star of s comma n, right? So my action would be half the time greedy, which is that I'm gonna assume that these are the numbers that I know of Q of s comma n, which is the state action value function. And if I know the state action value functions, the best thing I should do is any state is look at all the state action values for different actions and take that action with the highest value. Okay, that's greedy. Okay, and with some 1 minus epsilon probability, I'll just pick a random action. Okay, that ensures what is called exploration. Ideally, you can always pick random actions. Okay, so exploration is just so that you are not missing out on. It's the same thing with epsilon greedy. If you are not doing exploration, you will not know which arm is the actual best, and you'll be losing money. Okay. So that's Q learning. So in the next few slides, I'm gonna just summarize it. So start with some Q table, which is a state table of number of states times number of actions. The table that I drew a few slides ago. Let's say starting state is fixed. Let's say S1. For each time step, take an action uniformly at random with probability epsilon. With uniformly at random with probability epsilon, which is the exploration. Okay. In the sense, I'm going to disregard information, take an random action, or whatever values I know in the current state, I'm going to take the greedy action, because these are the numbers I think are the state action values. It's probably 1 minus epsilon. That's called exploitation of being greedy. Okay. And then I'll just update, because if once I take the action, figure out what the action to take, I'll give it to the simulator or the environment essentially. The environment will return back to me the next state and the reward. Okay, that's it. So given those 2 numbers, RT plus 1 and ST plus 1, I can do this update. Okay, of the current Q of S comma A. Okay. So new information is obtained, with which I'm going to update the current 1 entry of my table. Okay. And that's it. Repeat. That's it. This is Q learning. Okay. Notice here that there is no need for the model of the environment. We don't need to know the transition probability function. We don't need to know the reward function. But this procedure, hopefully over enough time, gives you good enough Q values, state action value functions. In the sense, hopefully these state action value functions are the same as little q subscript, little q star of s comma a, which were the optimal state action value functions. If these guys, by these updates, give us the optimal state action value functions, then we know how to go from optimal state action value functions to the policy, best optimal policy. It was just a greedy policy. Okay. So this is called temporal difference error. That's why it's written in this way, but you can think of it as moving average. And this is related to other family of other algorithms, so that's why let's not worry about it. Epsilon is the exploration parameter, similar to epsilon greedy approach in bandits. In fact, that's what we are essentially doing here per state, right? And the parameter alpha d is called the learning rate. It's like a gradient update. Okay. essentially it's like gradient update, right? You current value, gradient, update. It's not. Maybe next class we'll see whether there is some more connection to gradient updates. Maybe we'll see if it fits. Epsilon can be anything. It's user defined. For all epsilons, this will converge. Actually, that's my in the sense of somebody in 1992. Okay, Chris Watkins kind of said that for any epsilon, positive epsilon, you need to have exploration. Eventually, this Q table will have the same values as the Q star S comma A, as if you would solve the planning problem. Okay. See, if you did not know this Q learning algorithm, because there's long-term consequences of your actions, you can't just randomly. Earlier I was saying you can probably take random actions at every state, but it's not guaranteed that if you take random actions at every state, you reach all parts of the state space properly, so that you have good, you have good estimates of Q star. You can estimate Q star properly. Epsilon is letting you, it's like same thing with epsilon greedy. It's basically letting you explore. Maybe you will never take that direction, but it's also making you go towards directions where it thinks there is a high state action value, where the future, going from that point onwards, at least in the optimal policy case, from that point onwards, following the optimal policy will give you, tons of reward. Right? Expected return is what it is. Okay. Yeah.
So here we're picking basically two actions, action at time t and action at time t plus 1, right?
There's only one action. Either you choose the action like epsilon greedy uniformly randomly, or you pick the action greedily. This is one action in that one time step. Apply the action, you get a reward. You get a reward in the next stage. Update. Go back. Take another action. Update.
But inside when you have that max. So there
is no action. Previously there was a two action, but then I said I'm going to replace that with the max. Remember? There is no action. This action is just a lookup, right? This action is not being taken as such. This is like I know that I reached st plus 1. At that st plus 1, I have this row with q SA values. I'm saying which A has the highest value. That's this number. That's it. I'm not taking this action. I'm not giving this action to the environment. Any other questions? Okay, yeah. So, again, just so come back to just in terms of planning versus reinforcement learning. So, Bellman optimality equation, which involved a max operation. So, Bellman expectation equation involved just no max here. There was just there was no max here. Bellman expectation equation, which means that you had to specify there was a pi here, which was the given a default policy. A Bellman expectation equation would give you what is the Q of S comma A for that given policy. Bellman optimality equation just says, okay, replace, that was a non-trivial part where we said Q star of S comma A, which the Q star of S comma A is the state action value for corresponding to the best policy, obeys an equation where this is equality. Swap direction equality. Now, Q value iteration or value iteration was just saying, okay, instead of equality, what I'll do is I'll start with arbitrary numbers and plug this in here, compute this, go there, get new numbers, plug this here, compute this, go there, and so on. That was the value equation. It's just trying to kind of use that Bellman optimality equation as a way to generate, define the iterative algorithm. That's what Q value iteration did. And what Q learning essentially does is make this algorithm incremental. Just means that I don't have this expectation anymore. It just has to be one sample, right? I can only apply one action, I'll get one next state and one reward back. That was incremental. Okay, that was not incremental. Incremental just means one step, in the sense of I only care about S prime next state. Sample means I only take one action, so I only see one path instead of an expectation. and adding this epsilon greedy aspect to the problem. That's it. So this notation just means whatever the previous value is, take a weighted average of previous value plus 1 minus alpha times previous value plus alpha times this new value. So this is it's just a way to, here I'm just illustrating two update equations. One is for planning, where this expectation is basically capturing everything about the environment, and here you don't know the environment, so you don't know the script P and script R. So here you're just interacting with the environment, getting it's like a black box telling you what is the next state and what is the reward, and with that you are updating. Here black box or not black box, so here you know exactly what the transition probabilities and what are. So you can take an expectation given the current values and keep updating recursively. This will converge to Q star, this will also converge to Q star. This is a pure computation problem. There is no interaction in the environment because you've just been given everything. Here you really have to try, fail. Sometimes you may end up dying, for example, in the game setting, right? You may try different actions, the game ends. In the next episode, you try different actions, the game ends. From those, but in each episode, like every step, you can actually know what the S prime is because the game will tell you what the S prime is. You may have a current table of what in that S prime, what is the highest value that you can get, and so you can maintain this table and keep updating. But you may die, so in different episodes. As if you're an agent. So that's why you don't want to deploy, let's say, something like this in directly on autonomous vehicles. Maybe you want to have a simulator of the environment, traffic simulator, car simulator, and then work on it, and then the last level fine tuning you may be interested in doing this. Okay. That's it. So for today, we saw reinforcement learning. It ties back to bandits. Basically, context of the story. The biggest key thing is there's a long-term consequence of your actions, and that's what we are able to take into account because we are maintaining these objects, which are actually long-term objects, which kind of look at long-term rewards. The value function, state action value function, are really looking at long-term rewards, right? So that's why we are able to take into account this long-term consequence of a current action. And so in the next lecture, we'll kind of close the loop of this whole course and look at we'll basically, the reason I introduced Q learning as the only algorithm, there are many other algorithms, is because next lecture we'll try to use Q learning plus CNN as a case study. So next lecture will be a little bit lighter, I guess. So we'll case study, and so we'll close the loop in this course, and the examples you saw in the videos. So that's it for today's class. He replied? He replied?
I talked to him yesterday.
I have two questions.
Yeah.
First one was about the rejection sampling.
Yeah.
So actually, when we are doing the rejection sampling, we have a TQX, and for that one, I was just wondering because when we are choosing, thank you. Okay, so let's see this one.
1 second.
Yeah.